Today we're going to be talking about how to 3D print in metal on the MakerBot method. And I'm joined by my friend and colleague, Felipe Castaneda. Felipe, how's it going?
Hey, morning. It's always great to see you guys. Excited to be talking about metal this morning. So somebody actually makes tiny robots. That's also exciting to get to know your guys' applications. But yeah, it's definitely an exciting topic. We have quite a few parts, walkthrough of how to print with the methods. Any method will work with metal, which is to me unbelievable. But yeah, we'll be covering quite a few different things this morning.
Awesome. Yeah. Like Felipe said, we're super excited about the latest addition to our method material lineup, which is the BASF Ultrafuse, and we'll definitely be talking about that in a little bit. But for those of you who aren't familiar with MakerBot, we are a manufacturer of 3D printers, and in our newest lineup is the Method series. You've got a fully industrial capable machine that kind of fits in a desktop space. So it's not a huge refrigerator size machine. It could actually fit on your bench or your desktop. And it's packed with industrial features. Yeah, Felipe's got one right behind him. And this thing's got a heated build chamber. It's built like a tank. And we'll talk about all the different materials it can print in. But definitely popular in a variety of industries. We see customers all across the board, from healthcare, consumer products, consumer electronics, military defense, automotive, aerospace, you name it. And speaking of which, if you could take a second to fill out the poll and let us know which best describes you. You're either looking into getting your first 3D printer. You already have a printer, but you could use another or an upgrade. Have 3D printers galore. I'm all set. Or just interested in 3D printing, but don't really have a valid application use case for it. So take about 5 more seconds and let people finish filling that out. 4, 3,
While you guys
2.
fill it out too, it's good to introduce Alejandra. She'll be taking your questions behind the scenes. So if you have anything that comes up through the presentation, we'll be doing a Q&A at the end, but she'll be collecting any comments on the chat section so that we can answer those as well.
Good call. Good call. All right. And it looks like the results are in. Most of you already have a printer, but could use another or an upgrade. Cool. So
it's my favorite answer too, right? You never have enough printers. Like I got
You can never have enough printers. That's true. Felipe is trying to get like 3 more, I think, for his studio over there. So cool. Well, thanks guys for filling that out. Now let's go ahead and get into the agenda. So we'll be starting off going over just some of the basics when it comes to metal 3D printing, for those of you who are new to it. Then we will talk about BASF Ultrafuse 316L stainless steel, plus the MakerBot method. What is it? How does it work together? Felipe will be kind of walking through how to print with that. Then we'll be talking about switching between metals, composites, and polymers, because at the end of the day, the method platform, while it's really exciting that it prints metals, so we don't want to forget that it also prints composites and polymers, and we have a ton of materials for those too. So you can really easily switch between those and make some really unique, assemblies and do lots of projects. Cool. So and then obviously, like Felipe said, we'll get into a Q&A. So drop those questions in as we go, and we'll get to as many as we can. All right, let's get going. Metal 3D printing, the basics. All right, so with metal additive, I don't know why I keep skipping slides here. We've got 4 kind of families of technologies, if you will. So starting from the left side, powder bed fusion, that's kind of the original. Binder jetting, we've got direct energy deposition, and we've got material extrusion. And material extrusion we'll save for last, but that's what we're going to be talking about when we're talking about method. But I wanted to make sure everybody's kind of familiar with all the technologies that are out there. So with powder bed fusion, you're basically talking about DMLS, SLM, or EBM. These are all kind of variations of a similar technology, but basically you're using a laser to melt or sinter metal powder together, right? So you kind of see that in the image in the background, but basically it's gonna melt a layer, go around, design it, kind of hit the design with the laser, brush another layer of powder over the top and do the same. And so you're basically building that up layer by layer. With this, you get really good geometry, you get really high precision, wide range of materials, and the properties are really solid. Some of the cons of this are it's really expensive. The machines are super expensive. The parts have to be actually physically attached to the build plate. So you've got metal parts connected, basically sintered to the build plate. So you have to cut those off, and you have limited build volumes, and metal powder handling can be, can be dangerous, can be messy. So you just have to be super careful when you're using that technology. And this is something you would see like in an industrial, shop with like all the protective equipment and everything like that. The next technology is binder jetting, similar in the fact that it uses powder, but instead of the layers being sintered, you're actually spraying down a binder. You're jetting a binder onto each layer, and that binder is basically going to hold those sections together. Then you take that part out of the powder, you post-process it, and you do a final sintering run, and debinding and sintering, you remove that binder, sinter the part, and you get a final metal part. So some of the pros are you can use larger build volumes because there's no heat involved, so there's not going to be warping of this part. The parts are not attached to the build plate. You have geometric freedom. It's faster technology than the laser sintering, and it's lower cost than powder bed fusion. Now, cons of this one are the post-processing steps requires debinding and sintering, high cost machines, again, more porous parts, so lower dense and also lower density parts. You have less material selection, and you're going to have less accuracy due to the shrinkage you have in the furnace from that post-processing. Sorry, I'm going through these kind of fast. I didn't want to give like too much info, but I do want to be conscious of time. So let us know if you have any questions that I miss. Direct energy deposition. This one is basically you're taking a metal wire and you're basically, it's almost like welding it, on a surface. So you can actually print this onto the surface of something else. And oftentimes you'll see like a robotic arm or like a 5 or 6 axis, kind of gantry or arm that is laying this down. And metal wire is actually the most affordable metal material. It's kind of a standard material commodity that you can get. It doesn't, I guess, some of the other pros are you can actually use multiple metals at once. I mentioned the multi-axis axes that are available. Larger build volume is possible. It's super efficient in material use because you're just kind of using that metal wire, and that is like going to end up in 100% into the part. It's fast. Some of the cons are the surface quality could be worse. Think welding, you could have like a lot of scarring and stuff like that. Small details difficult to impossible, and high cost of machines and operation. And that brings us to material extrusion, what Felipe and I are talking about really for the most part 99% of our time at MakerBot. And that is the key benefits here. Well, I should say how this works for those of you who don't know. You're literally just heating up some filament and extruding it out of a nozzle. And in the case of Ultrafuse, that's a pre-bound filament. So it's a binder plus metal, and you go through kind of those post-processing steps to remove it afterward. Pros here are it's by far the most affordable from a machine standpoint and a material standpoint. It's the most accessible too, because you can use a MakerBot Method 3D printer, which we're talking about. This is a machine that starts at $4,000 compared to the previous 3 classes, which you're not going to be able to get into for, you're talking about hundreds of thousands of dollars for those machines. So not really in the same stratosphere when it comes to costs. This is a much more accessible technology. It's easy and safe to operate, and the machine is, in the case of Method, it's compatible with other materials like polymers and composites. So it's not just a one-trick pony that's only printing metal, but you can have a variety of materials. Some of the cons are that post-processing steps, which we'll go over later. You have some more restrictions on geometries. The parts are going to be somewhat lower densities, although, we're still talking about high 90%, maybe 96% plus in terms of density. So still pretty high density parts. And lastly, you do lose a little bit of accuracy. You have to kind of adjust, I guess, for the shrinkage that you have in the furnace when that binder is removed. Okay. You know what? This is kind of a long section, so I'm just gonna kind of fly through this, but just wanted to also highlight the differences of additive and subtractive for those who are new. Additive, I think it's pretty obvious in the name, but additive, you're basically building layer by layer on top of each other to create a part out of nothing. Subtractive, you're starting with kind of your blank of material, or like a block of aluminum, and then you machine it down into a part. So you end up with kind of more waste. And that's kind of, I guess, the key things to really know between these are, with additive, you avoid a lot of waste. You can make more specialty customized parts, and you just have more geometric freedom because you don't need a tool head to like navigate within a part and get to like odd angles and locations. Whereas with subtractive, you're a little bit more limited in geometry. But some of the benefits of subtractive are that you can get, really clean finishes. Some of the most precise parts you can get are for machining. You can also machine additive parts to like finish them. It's a relatively fast process to actually run the machine, but the setup of the machine can actually be pretty laborious. Like, you might have to create multiple different fixtures, which in themselves might require machining and tooling. So it is, it's just something to think about. Usually machining requires a little bit more specialized skill set. You need a machinist to run CAM and to who really knows how to like, put a part into a mill, switch it out into a CNC, and kind of like do all these different passes on the same part. Whereas with a 3D printer, you're literally just taking the CAD file, hitting print, and that part is done in one pass, and you don't need to make any adjustments throughout. So sorry, I didn't cover all this detail. It's probably overkill. You can look it up if you want later on. So anyway, that is basically the intro to metal. And now Felipe has been like sitting tight there, but I'm going to basically turn it over to him so he can kind of walk through BASF Ultrafuse 316L and MakerBot method.
Thanks, Sean. No, I mean, I think it's always great to have like the good overview and a solid intro, so that we're all like in a plain field talking about metal. But yeah, so excited to talk about how it works with Method. I've been seeing some of the questions come in, whether we are offering custom slicing settings. We are, where we are, what's the process? And not only the process, but also, what the parts look like. And I have a few parts. I'll share my screen in just a second. But for now, like, to get started with metal with MakerBot, you'll need basically three things, right? That's the MakerBot method. Any one of our method printers will do, meaning the regular method, Method X, or any of the carbon fiber editions will work with metal. Since you need the heated chamber to go to 60 degrees Celsius, so all of the printers will have that range of temperatures. Second thing, you'll need the Labs Gen 2 extruder. So I saw some of the questions, asking whether the Gen 1 is going to be able to work with it. It will go to those temperatures. The wear in the extruder might be a little bit faster in the Gen 1 versus the Gen 2. but it should work okay with metal. And finally, you'll need the material, right? Which in this case is BASF's Ultrafuse. I have a spool here. It's hard to combine. I wish that we could just send samples of these to everybody, right? But this thing is freaking dense. So every spool of it, it's about 3 kilos. So close to, what is it, like 7 pounds almost. So it's a really dense material. I mean, this is the real stuff. And as Sean was describing, it's essentially the metal alongside polymer agent, which is what allows us to extrude the filament through, or to run the filament through our machine, right? Following the same process as you would with any other filaments and materials that we currently offer on the Method platform. If you go to the next slide. Now, once you have those 3 elements, right, the printing process is fairly straightforward. And we've been seeing a lot of questions on social media, you know, how easy it is it really like printing and that's it? And I'm going to show you a few examples of what the process looks like, because there's definitely a few extra steps after you printed the parts. But we split it into 3 main sections. Essentially, the first step is to print your part. That's what I was describing earlier, just with the BASF filament. And you'll get your, what we're calling the green part. I'm going to also be toggling back and forth between my webcam and my sort of side cam, let's call it that, to show you some of the parts that we printed so far, that I printed right here in my setup, right? So you are going to be printing your parts in your method. That's, you know, any one of the methods with the lapse extruder and the filament, and you'll be getting what we're calling a green part. These green parts, essentially, if I had to describe them somehow, I would say they feel really close to ceramic, right? It's kind of like that same texture. They are definitely much denser, and you can already tell that this material is way different than any other type of material. But yeah, you get like the same precision that you would with our existing materials. However, in this step, the first thing to consider is that since later on these parts will be sintered, right? They will be basically cooked up in an oven. You will need to accommodate to some shrinkage factors. That is, you know, the guidelines that we're talking about is about 20% in X and Y axis, about 20% in the Z axis, due to the shrinkage, the size that, you know, how much the shape will change when it's sent to the sintering oven. So that would be the step 2. You will be sending your green part to Matter Hackers, and that's what we see here in the diagram, right? Well, in this case, Matter Hackers, that's the service that we've been in contact with the most. There's a few options of how to sinter your parts. You could get your own sintering oven. Those are massive machines, and I'll let Sean describe those in a second. There's a few reasons why you wouldn't want to have your own oven, but in this case, what we have been recommending is to send the parts back to Matter Hackers. In this case, whenever you buy the filament, the BASF filament from Matter Hackers, you will also in your purchase, you'll include the purchasing tickets. Those are essentially, well, as the name suggests, just tickets that will allow you to send back parts to Matter Hackers for them to sinter those green parts. And by sintering, they essentially put the parts in a massive oven that gets heated up to about 13 or almost 1400 degrees Celsius, and in a pure hydrogen environment. And that basically cooks up your part, right? And after the sintering and debinding process is done, you'll end up having the final part. You'll receive that solid metal part in as little as 5 days. So I would say like ballpark, like a week or so, to get back your part. And as you can see here in the video, and I'll be jumping back to the camera as a, you know, a bigger sort of whenever we jump out of the screen. But you can see already like the size difference that happens between the green part and the sintered part. So this is my green part, the one that I printed on the method. This is a part that I got from Matter Hackers. So I'll be showing the detailed shots of that in a second. But if we go to the next slide over right now. Now, to cover the actual printing process, let me switch back to my main camera. Here we go. So to cover the printing process, right now in Cloud Print, we are about to launch the update for Cloud Print, specifically our slicing service, our online slicing service for you to print metal. But essentially, you're selecting, and if we, maybe Sean, if you allow me to take over for a second.
Sure.
And I'll share my screen with you guys. Here we go. So I'm here in Cloud Print. And as you can see, once I selected my method printer, I'm also able to select, let me simplify the view a little bit. So I got my same part here, right? This is, it's essentially the tip of a gripper that I designed. There's a few elements that I had, that I designed in here that are not machinable. There are also, it would be just really expensive to produce in any other way that's not 3D printing. But, you see like this fading, diamond, texturing, just to add some gripping element to the part. Apologies for the doorbell. But yeah, you bring in the part here in Cloud Print, and then you just select the type of printer that you will be using, the extruders that you will have. If the printer is connected, it'll automatically detect the last extruder. And here in the drop-down menu, you can already select metal for you to use, right? When you select metal, a few changes will happen on the back end. And for those of you asking, it is mainly about the print temperature, the chamber temperature, but there's also certain changes that happen in the print speeds, right? Because since we're printing this material at 100% infill, it's essentially solid, right? And we have to be very careful with how fast we print it so that it doesn't warp and essentially deforms your part. But all of that processing is taken care of by Cloud Print. The one thing that you will need to be cognizant of is the scaling element, right? As I said before, the sintering will shrink your part about 20% in X, 20% in Y, and 26% in Z. It depends a lot, and it's tied definitely to the size of your parts. So I was just describing the scaling part and the fact that you want to have parts that are, essentially flatter, flat and extended as opposed to really tall. There's a limit also on the size of the oven itself, right? So you will need to print parts that are under 100 millimeters per side, so 100 by 100 by 100 millimeters. And that's due to the fact or the sizing limitation of the sintering oven. Anything larger than that, and then, it's not going to be, we're not going to be able to process those parts. If you want to jump back to the deck.
Okay. I got it. All right.
And then the next slide over. Now, to talk about a few of the specs of the material, and I'll be coming back to some of these parts because I'm sure that you guys have a few questions on them. But it's incredibly, the temperature resistance is incredibly high. If you think about ABS, that's about 180 degrees Celsius. Here you are going all the way to 550, 561 megapascals in the tensile strength, so way harder, and then the hardness itself, 128. It's going to be noticeably harder. It's this material, and that's another thing that I really like to do. It's just so you guys get an idea of how metal these parts are. Like, just the sound that they make, right? It's like the density of the parts. It's impressive. And also, speaking about density, I have my little scale here because let me change again to my handy side cam. So I've got this gripper assembly here. And as I said before, I was printing just the tips of the gripper in metal because I didn't want the whole part to be metal, because if I weigh, here we go, bringing the scale closer, zeroing it in. Oh, let's put it flat. There we go, 0. So if I weigh just this whole assembly, and this assembly is printed out in carbon fiber, right? All of these components, that comes out at 123 grams versus just the one gripper, right? The one tip here, which comes out at 67 grams. So for those two tips, I'm going to be having about the same weight as this whole assembly, right? So I guess, what I'm trying to say here is just giving you guys a clearer view of how dense and how solid these parts will be, right? Oh, instead of the slide? Sure, you want to jump back here, Sean? So here we go. So that whole assembly is 123 grams. And if I bring in just the tips here, that's 130 grams, right? So the density, you can imagine the density of the material of these two parts compared to the carbon fiber parts. And that also speaks to the fact that, all of these parts have been printed on a method, right? That's one of the really key things to, I think, that impressed me the most. The fact that I don't need to be using a different machine to print the specific metal parts when I need them, and then the specific nylon carbon fiber parts when I need them. I think that that's one of the most interesting features of the whole set. Also, speaking about the, we might, or you guys might see that the material is potentially you can use it in other systems. However, the accuracy at which that method has is what makes this proposition also really interesting, because if I take my original part, so this is another green part that I have. It's essentially just an outer ring for a planetary gear system that I'm printing. This is a scaled up version of it. But the accuracy that you will be getting because of methods heated chamber. So I'm going to go ahead and measure this part in one of the axes. So that's 80.9. I think that you guys can see that there. Rotating my part 90 degrees, measuring it again, 80.9 again, right? So what's happening here is that my green part is getting a much higher resolution, well, not resolution, but accuracy, because of the fact that I'm using the method, right? And by having a tighter set of tolerances on my original green part, I'm going to some extent, get a much better result when sintering, right? As I said before, you will get some shrinkage when you sinter the parts. For example, in this specific one, the outer edge, the sleeve of this gear system is also nylon carbon fiber. The inner gears here, those are printed in ABS. But you can see, let me bring this closer to the camera. Because there's a small gap in some of the edges of the part due to that same shrinkage, right? So I'm usually, when printing with method, when I want a tight fit, I will use about 100 to 200 microns of an offset. With metal, I would recommend increasing that all the way up to almost 0.5 millimeter, so 500 microns, just to be safe. Another option would be to post-process your part, right? So once you have your metal parts back, and we'll be talking about those assemblies in a second, but once you have your parts back, this is essentially solid metal. So anything that you would want to apply on a solid block of metal, you can do with these metal parts. I saw that. Can we see the printer in action? I'll show it in a second, but first I want to jump back into the presentation, kind of to finish covering the slides that we have, and then jumping back into the show and tell section here.
Yeah. See that?
Yep.
All right. Cool. Yeah.
Oh, right. So this is how the actual ticket looks like, what I've been referring to as a processing ticket from Matter Hackers, right? So you'll weight your parts, you'll number your parts, you'll know how many parts you're sending out. And essentially you fill up this form. Matter Hackers will send it to you when you purchase the material and send it back to them. And this is what, this is all there is, right? You basically send back the parts, the green parts, as I said before, labeled, numbered, weighted, and then you get back the metal parts.
Cool. And then, this is just an image I threw in. This is an example of what you're going to see, what the facility is going to look like. This is a debinding and sintering oven. So, it's probably the size of an office or a bedroom. So, it could be difficult to get one of these for yourself, hence the desire to send it out and have, a service bureau do this. It's really exposing these parts to really high temps and pressures. I think it was 1380 degrees Celsius is what the sintering takes place at. So, and this is just kind of an overview of the process from their end. They receive the part, they weigh it, they kind of match it up with your form to make sure it's consistent. Then they use these ceramic plates. These are kind of similar to the build plates on our 3D printers, but they're sintering plates. They spray a coating on so it doesn't stick to the plate. And these plates, as Felipe pointed out, I believe they're 100 millimeters by 100 millimeters. Is that right?
Yeah, so that's to answer, I think it was Eric's question, saying like, what's the limit? Because the oven looks so massive. It's basically, you could fit an entire person in there. but the actual plates that you can see there on image number 4 and image number 10, right? It's where they are most clearly visible. Those plates will be hosting your parts while the debinding and sintering takes place. Anything that gets outside of those plates, and that's defined by them, right? So anything that gets outside of the plates, it's just not, they are not able to process it.
Yeah, exactly. And so it's like, it is a two-step process. The debinding actually happens. They take it out, they weigh the parts, and then they put it into the furnace and they sinter the part. And the debinding is where you're removing that binder. Actually, just a little fun fact, the green part then becomes a brown part once it's debound, and it's super, super fragile. So if you drop that thing, it's gonna break into a million pieces, because it's basically like unbound metal powder at that point. It's probably like clay. And so then you do the sintering, and you end up with a solid stainless steel 316L stainless steel part, which is, you know, a really common type of stainless steel. It's not just some kind of, you know, composite that was invented specifically for 3D printing. The end result is real 316L solid stainless steel, which I think is the coolest thing about this material. All right, speaking of materials, we'll just quickly go through. I think Felipe showed kind of the benefits of creating an assembly with multi-materials, having that lightweight factor, along with, you know, the benefits of metal where you need the metal, but not where you don't need it. And I think the gripper is probably the best example for an end of arm tool on a robot arm. You know, you need to minimize the weight, because those robot arms, even like the largest UR arms, you know, their payload is like 10 kilograms, I think. So, or yeah, like 22 pounds. So not a lot. So if you're using a full metal end effector and it's 10 pounds, you can only pick up, you know, 12 more pounds. So you want to minimize that weight in that kind of a case. But there's a lot of other examples. You know, automotive, always trying to minimize weight, especially when it comes to motorsports. And we work with a lot of racing teams, so they use a lot of carbon fiber parts, as you know, I'm sure a lot of people are familiar with. Yeah, then when it comes to materials for method, so we talked a lot about the BASF Ultrafuse 316L, but what's unique to this platform versus all, you know, pretty much all the other metal technologies is that you can also print composites. And for method, we've got 8 composites that are basically ready to go. And then we've got a whole list of polymers as well. So composites, you're talking about nylon carbon fibers, ABS Kevlars, ESD materials, ABS and PETG ESD for, you know, highly sensitive electronic housings and stuff like that. And on the polymers front, you've got ABS, which is kind of, you know, a true standby. And with the method's heated chamber, you can actually print real ABS dimensionally accurately with guaranteed precision of, you know, plus or minus 7 thousandths of an inch, which is unheard of for ABS unless you're talking about industrial 3D printers. Nylon, you know, the list just goes on. So it's super easy to do that. You actually, okay, never mind. I thought we had another slide, but you can actually just swap the extruders. We have 6 different extruders for it. I think Felipe's got one on his camera. Which one's that?
This is a labs extruder. Actually, you know, if you guys, now that I see a lot of comments talking about the materials that you can print on, if you want to answer just that quick question on which material interests you the most. But for me, it's the craziest thing is just being able to have the one machine that can print it all, right? We've all, you know, we are here all familiar with machines that are dedicated for metal, that are dedicated for carbon fiber. But the fact that Method can just toggle between, you know, let's see, somebody was asking about flexible filaments, and I'm working on this little tire model, scale model that I printed in the SEPS material. This was printed on my Method. The fact that I can print nylon carbon fiber, because I wanted, as Sean was saying, I'm creating like this like lightweight robot gripper. I'm just using an EMA 17 motor here to run it. This was printed on a Method. And then the tip itself, that's kind of the new addition, but the tip of the gripper, because let's say that you wanted to have something that's even more resistant to wear and tear, to the abrasion that the gripper itself might be encountering. This was printed on a method as well, right? Okay, yeah, and clearly based on the results in the
shocker.
yeah, exactly. Everybody's super interested in the metal, and I am, I think that I am also. It's, how do I say this? Metal is amazing. Like being able to print metal, I think has always blown my mind to some extent. But being able to do so in a platform that allows me to, I'll say play, but it's not playing. I just enjoy it too much. But in a platform that allows me to print in anything from something that's flexible to something that's solid metal. That's, I don't know. It's come a long way. At least I've been a fanboy of 3D printing for a while. And it's the really exciting thing about Method itself, right? That we're not talking about a dedicated printer that sort of sets you or locks you down to a single path material-wise, but one that allows you to print successfully in a range of ways, right? It's essentially what Sean was saying. We're just changing the extruder, and all of a sudden you have almost what I would describe as a new machine. So
yeah, it's super versatile, and the platform itself is industrial. So you've got high precision parts with guaranteed dimensional accuracy, and that makes a huge difference too. You've got a heated chamber that increases strength even on the polymer side. So I mean, we could talk about this forever, and we should probably continue on because we have a ton of questions. I did want to mention one other thing though. The when you're talking actually about a pure cost breakdown of the metal prints, I thought this was super interesting. The time and the cost of printing the part and sending it in for sintering, which is certainly a new step for people who may have 3D printed with like regular polymers in the past, the fact that you have to send it in. But when you compare that actually to having a 3D printing service print your parts out of metal, I mean, you're actually cutting your costs by up to 5x plus. I mean, depending on, in this case, we took quotes from some of the leading service bureaus, and a part printed in the exact same material, the Ultrafuse, with kind of the same drawbacks that you would have or the same pros and cons, is 5 times more expensive. If you tried printing that part using DMLS, the powder bed fusion that we talked about, you'd have about $1,200 for a part. And we're talking about $80 for the part, which is like the material, that you print into the part plus the sintering costs. So obviously you have the upfront cost of the printer as well, but if you're printing, a handful of these parts, it probably is going to make a lot of sense for you to just go ahead and get a printer. And even a machine shop, it's even super competitive with getting a part machined out of metal as well, because the costs of having a machinist do that, I mean, that's not cheap. So anyway, I just wanted to throw that out there as another kind of benefit of the Ultrafuse method. Cool. And Felipe, do you want to tell our audience about our latest promo that we have going on here?
Yeah, so right now with any one of the method printers, you'll be getting a free lapse extruder. So that's essentially what you need to print with metal, right? Just a lapse extruder. And not only that, there's still the ongoing promo. It's like 25% off of any method. I want to talk more about the parts themselves, because I quite have a few parts. But seriously, if you're, as we mentioned originally, if you're like me, just considering getting an additional printer, I am biased because I work for MakerBot, right? This is a freaking beast of a machine. I mean, yes, I'm saying it that way, but it's so nice to be able to jump back and forth between the materials, and that's what I'll go back to. But if you're interested in getting one, now it's a great time just because of that discount. And then on top of the discount, there's also the free lapse extruder. That's what enables you to print with metal, right? Somebody was asking like, okay, so how many extruders do I need if I want to keep jumping back and forth? I think that's a great question. And we'll be getting to the questions in just a second. But the way, I think that the analogy that we've been using, it's essentially like a drill bit, right? You have one drill, but you're not going to use the same wood bit and the metal bit and the concrete bit for any, for the same hole. And that's essentially what we're doing here. We're just changing the tip of the machine so that you can have a dedicated element to cover for that particular material. Why? There's a few reasons, starting with the type of material that we're talking about. Let's say metal is going to be much more abrasive than, for instance, PLA. And also, and this is also, part of my personal experience using the machine, you don't really want to be jumping back and forth too much with the same extruder between materials, even if you could do so, because since they have different temperatures, printing temperatures, they will definitely, you get to a point where you can cause clots on the extruder because of the fact that, let's say, you print on ABS, which prints at 260 degrees Celsius, right? And then you jump back to PLA. That effectively will leave a little bit of traces of ABS that will not be able to be melted out by the PLA. So that's why I think it's just a cleaner experience to have dedicated extruders, and it's part of why we really recommend having these sets of extruders just to get the proper results. And I'll remove my face from the camera because I want to, as we answer the questions, I want to keep showing you guys like the resolution that we're getting on these parts. So I'll be telling you what these parts are while we read some of the questions, but this is another green part. I was just testing out the, kind of the types of texturing that we could do and the precision that we could get. So it's still not sintered, right? It misses to be sintered, but I was just testing out like undulating elements also here on specifically on the gripper, and I wanted to show like a close-up of it. Just the amount of resolution that you're able to get of the material, it's just something that, this is not machinable because of the way that it's embedded here on a concave surface. It's not going to be, there's no other way to do it outside of 3D printing. And the fact that you're getting this level of resolution with the printer, and that resolution is also present, on the sintered element. I'll let the camera focus for a second.
It's kind of hard to see the detail, honestly, but
yeah,
it is there. We might have to take your word for that.
Let's see if I allow it.
We need to get you like a 4K camera, I think.
I know, right? Just like something that has a manual focus element.
Yeah, that would be a Mac.
Yeah, quite a few. One thing also to consider when printing metal, you really don't want to print, to use supports, or if you're using supports, you will want to design them yourself. So any part that's self-supported like this one will print just fine, but you have to think of the fact that any support element will be, if it's needed for the sintering process, then it will become also solid, and essentially it will become almost impossible to remove, or you'll have to machine it somehow later on. So another important thing to consider, right? That's whether you're using supports or not. And if you are, that's, most likely than not, you will need to design them yourselves manually. But with that, I don't know if you want to jump into the questions, Sean. And
yeah, let's bring in Alejandra.
Yes,
we have any questions there?
Oh, we have 1,000 questions, guys. We apologize in advance. I know that we won't be able to go through all of them, but we'll make our best. We'll try, and if not, you can expect an email with your answer. Okay, so Felipe and Sean, do you know approximately how much does the metal spool cost?
I think it's about $500 on Matter Hackers.
Mm-hmm. Okay. And Felipe, you mentioned that it's like 3 kilograms approximately, but how long and how much per spool for cost?
So all of the parts that I've shown you before, I haven't even run through half the spool, right? So I don't have a specific number. Well, actually, the best ROI calculation is what Sean was saying, right? That those $80 were amounted for printing out this particular gear. So this is the gear that we quoted out, and it's $80 worth of the material and the post-processing, the sintering and everything. So that would be my kind of ballpark. It takes you a long way. It's hard to tell. It depends a lot on the application, but I would say if I jump back here to my,
I'd say one thing is that the parts are 100%, dense. So keep that in mind. Because sometimes with the polymers and composites, you can print with like 10% infill, and you actually can print way more parts because they're not, if you're not printing solid. But with metal, you obviously want to print solid. You actually have to print solid, or it's going to fail on the sintering.
Mm-hmm. like the other, just like eyeballing reference is like all of these parts have come out of this pool and I'm not even halfway through.
Yeah,
So
if
that
that
tells you a little bit more.
Yeah.
Okay, I think that answered a lot of the questions they were asking. What is the infill required when printing with this?
Yeah, you should use 100%. And that's not only because of the fact that you want to have like solid parts, but also if the part is not solid internally, then it can compromise the sintering process. If you can imagine the fact that anything that's not self-supporting also internally can collapse under its own weight. So these parts are really dense, right? So by making it entirely solid, basically you're creating a self-supporting structure inside of the part itself. It cannot be a hollow part.
And if you use the metal setting in Cloud Print, it's just going to default to that solid fill anyway. So
yep.
I would highly recommend using that because they've done a lot of testing and there are a ton of settings that were changed specifically for that material that don't always have to be changed for new materials. So I would highly recommend leaning on that testing and research.
What is the maximum thickness that can be printed without distortion?
That's a trick question because it depends a lot on the geometry itself, right? I've shown you, for instance, this gripper. This is about 10 millimeters in this, like if you take this cross section, right, will be about 10 millimeters by 10 millimeters. The gripper itself, because it's not an even shape, distorted a little bit more, slightly more than this circular element, right? The more even your part, the less distortion you will have. So there's no clear answer. You know, I also have like this double pipe feature here. You can see how it's slightly branched out, like basically it's doing almost a split a little bit. It depends a lot on your part. There's no specific answer for that. I would just default to that, you know, 20% on X and Y, 26% in Z. But if you're having parts that will interface with other components, like in this assembly, you're going to be better off sintering the parts first, having them come back to you, and then making any adjustments if you don't have enough tolerances available in your assembly.
We have a ton of questions regarding shrinkage. So how precise is this shrinkage, and does slicing software compensate for this shrinkage when you're designing?
Not at the moment. We are trying to figure out if that's because, you know, as I said, it depends a lot on the part. The ballpark is 20 by 20 by 26. As you can see here, actually, this is a good example again, not to bring back the same geometry, but here, you know, the way that this part nests, I didn't do any changes into my spec here when I was building the final assembly. And the part does fit in nicely, nice and tight. You can also see how here, there's a little bit of a gap, right? It's hardly visible on the web. There we go. A little bit of a gap. If I align it there, then the part will protrude slightly here outside of my part. It's about 200 microns. So it all depends on the geometry of the part. It's not covered by the slicing settings. You will have to change those yourselves, but it's about 20 in X and Y, 26 in Z. That's due to the weight of the part itself, bringing the part down. But you won't see, we're not talking about millimeters off. We're talking about probably 200, 300 microns deviation, depending on your geometry.
Okay, and also a lot of questions regarding support material. What support material is it used for metal printing? Do you recommend it?
You shouldn't use support. Well, no. Okay. No, you have to print with a single material. So you cannot sort of use, our soluble material here and mix it up with metal. You'll have to do it 100% with metal. So that means using either breakaway supports or custom model supports or geometries that don't require support. So all of these parts didn't require any sort of supports. I think that's the easiest and safest way. It's just like with any new technology, there are certain things to keep in mind. In this case, if you don't have a geometry that's self-supporting, like even this one, right? This double pipe, it's still self-supporting, so it can be printed out like so, and then essentially sintered in the same way. But you cannot use soluble supports for these type of parts.
Also, questions regarding how fragile are the green parts. Are the green parts strong enough to take the beating of shipping? And how strong is just the green part if you didn't end it up in sintering?
Yeah, I don't think so. I've been getting this question a lot, like, hey, can I just use the green part as if it was the metal part? That's a big no-no. You want to sinter the parts. Having said that, and I was actually waiting for this webinar to do this because I haven't really pushed the part all the way to the limit. But if you want, it's not a cookie, right? It's, oh wow. I mean, it's pretty strong. This is of course not in my, it's far from being a like scientific experiment, but I would not use the green part as is. You want to sinter the part because you really want to get rid of that binding agent for it to be 100% metal. This part is not brittle. This part is pretty damn strong, but it's still not metal, right? It's not what the end goal here is.
How do you think it compares to like a carbon fiber if you know, because that would be like an alternative if you wanted to print something. I think a lot of people think they need metal, right? And they can often use carbon fiber for the same.
You're exactly right. Like, for some of these elements, carbon fiber might give me enough strength. Like, all of this assembly was done initially with carbon fiber, and that's more than strong enough. So you don't want, it's part of engineering, right? You don't want to over-engineer something. You don't want to overkill the part. So sometimes you're better off with just doing something in ABS or in carbon fiber, because these parts are already pretty damn strong. If you need that extra layer, then metal, but only where it's needed. And that's kind of where we keep going back and forth with this whole sort of mixed material assemblies, right? It's another tool in your tool belt and under your belt, but it's not the end all be all. It's just important to keep that in mind. You just use it when where you need it.
And going back to that mixing materials, can you mix the Ultrafuse 316 with water soluble scaffolding material like PLA?
For printing and processing it, no, because
imagine like PVA, right? PVA.
Yeah, like imagine, like as Sean was saying, the sintering temperature is about almost 1400 degrees Celsius. PVA will melt at about 120, so 10 times that temperature, right? You cannot cheat the need for supports here. Either you design them yourself or you use parts that are self-supporting. And some of them can be rather complex. I'll bring one other part while you give us the next question, Alejandra. But if you think about some of these lattices that you can print from a method, just like it can get really complex even without using supports, right? So this is just, a lattice cube that we printed out in the method as well. So you can print really complex elements that are not machinable, that have to be 3D printed, but still don't require any supports.
Okay. What are the tolerances after sintering? And is the final result non-porous?
I mean, it is a labs material technically, so we don't give any like guaranteed dimensional accuracy on the labs materials because they're by their nature third party, and we haven't done quite as much testing as we do on kind of the MakerBot materials, which we do guarantee dimensional accuracy on. In fact, MakerBot, you'll see that like when it comes to like desktop 3D printers, it's probably the only machine that has guaranteed dimensional accuracy on any materials. So, the fact that we don't have it on the labs ones is not that unusual. Like, you're not going to see that from any machine guaranteeing a spec, especially for the Ultrafuse, because of the variability of the depending on what the geometry is, and it's going to shrink at different rates depending on what that geometry is too. So
right. It's going to be hard for us to commit to anything, but I would take you guys back to this specific example, right? It's just like the fact that you're starting off on a much more solid point. Again, it's 80.8, and then rotate it 90 degrees, 80.87. So it's that sort of better starting point that even if you were to use the same material in a different printer, you will end up getting different results. So we don't have a specific dimensional accuracy because of what Sean just described. but the method is already robust enough to make you get much better results from my perspective.
Okay, a lot of people are asking, how is the dividing and sintering priced? Is it based on weight or size? And
It's actually
how long is the average part needed to be sintering in the oven? And what is a typical turnaround?
3 questions. What is this based on? The turnaround time and the oven temperature.
Time, I think.
The time in the oven.
Oh, the time in the oven, right? So first question, it's actually done by weight. Every ticket will cover you for about 1 kilogram of material, so a third of the spool. It doesn't really matter the amount of parts that you're sending back.
You actually buy the tickets up front, or
you have to. You can buy it later on. It's every ticket is $50.
you buy it before you send it in.
Yeah,
right?
yeah. Mm-hmm. You have to buy it before you send it, and then basically that ticket, you fill it up by hand, put it inside of the packaging or inside of the package that's going to be sent out. And it's $50 for any number of parts that will fit within 1 kilogram of material. So it's 1 kilogram of material for $50, regardless of the number of parts. Second question, the temperature in the sintering oven, it's
the temperature is 1380, the temperature.
The time.
The time I'm not aware of, honestly.
Yeah, I'm not sure of that either. But I know the time from like the best time you could get is, so the way they run it is they run it in cycles, and I think they run a couple cycles a month. So if your part gets there, I think it starts like on Monday or Tuesday. So if your part gets there like before that cycle run, you could get your part back in as little as a week. Which is really impressive. But if you just miss that beginning of the cycle, so you send it and it gets there on Thursday while the cycle's already running, you might have to wait 2 more weeks. But Matter Hackers, they publish the dates of when those cycles run, so you can time it accordingly and send your parts in, and just plan for that.
For one of our last questions, can you speak to the tensile strength of the resultant part? Is it a percentage less than a part with the same geometry that was machined?
I know
we have, I don't know how it compares to a machine part. A few things to keep in mind is that these are, of course, 3D printed parts, meaning they will have some anisotropic behavior to them. Since these parts are layered, then the strength of the part might not be equal in all directions. But there are certain parts, and this is where it's a tool for the right job. There's parts that you cannot machine. There's parts that you cannot, laser cut. It's just impossible to make it in any other way that's not 3D printed, right? If for whatever reason I needed to have this internal lattice in one of my components, there's no way, there's no casting, there's no machining. So it all depends on the application. How it compares percentage-wise to such a part, I don't have a direct answer, but if you go to makerbot.com/metal, you'll be able to download this data sheet that Sean is pointing to on the specific tensile strength. But that already, I think that
I mean, if you know anything about how like steel works in general, like if you get kind of a pure piece of like rolled steel, like that's going to be stronger than a cast piece of steel because the grains are all pre-aligned up. Whereas like when you cast it or you sinter it, you don't have kind of the alignment of grains to begin with, and also with the 3D printing layers. But also with the sintering, I mean, something unique about metal printing versus maybe some other polymer printing, the sintering will actually really bond those layers together much, much better than, say, if you just took a part off of a printer and you kind of have those layer line seams. So I think, it is still way stronger. I mean, our next strongest material, I think, is carbon fiber, and that's less than 200 MPa, I want to say, in tensile strength. So, and the max temp of that, the heat deflection temp of that is less than 200 also. So, I mean, I guess unmatchable properties here when you're comparing to some of those materials. But not everybody actually needs those specs. Like these are pretty ridiculous specs. So
it all depends on the application.
Can the finished part be welded?
That I don't know. I mean, it is 100% 316 stainless steel. So
I think it can. Yeah, I think you can do all kinds of post processing. You can machine it. You can drill it. You can.
Yeah, I saw somebody asking about threading it. You know, definitely you can add holes on the part and then thread. This is solid steel, so or close to solid.
Anything you could do, pretty much. Yeah.
And just for a last one, a couple people were asking, how do you fit the spool into the printer?
You have to side load it. It's the printer itself has a side port. I can show you guys if I'm sorry, I'm a little bit like tied up to my webcam. Yeah, but you can see, if you can see like that protruding thing on the side of the printer, that's my side mount for my external spool. And essentially it allows you to route a material, third-party material. That's not only metals, but any third-party material that you want to use in the method, you can route through the aux port, right? The method materials are hosted here in our material base. That keeps them sort of dry and happy. In the case of metal, you will have to route them through the side as any other third-party material would.
All right, we should probably put a fork in it there. I think we're a little over time here by like 4 minutes, but I just want to thank Felipe for joining me on this adventure. It was a lot of fun to talk about a new material, obviously something that's as exciting as metal. It's clear that everybody on here finds it exciting with how many questions we've got. And if we didn't get to your question, we'll try to email answers to that. Who knows, maybe you'll get a call from me later today and I'll try to answer, or Felipe. But yeah, thanks everybody for joining. Thanks for all the questions. And if you have any other questions, feel free to email us, hello@makerbot.com. Forgot to change out the link, of course, makerbot.com/carbon. That's our carbon fiber edition, which you can print metal on as well. So same thing there, or you can go to makerbot.com/metal, see some of the same info that we presented here today. If you want to share it with somebody else and kind of get a quote, you can request a quote there as well and talk to a sales rep. So yeah, thanks everybody. And until next time.
Thank you guys. Have a good one.